Start again. So it's a pleasure to have here Angélica Osorno, who will talk about two categorical opfibration, Quillen's theorem B, and S localized S.
Yeah, or S inverse S. Yeah, thank you. Thank you, Joachim. So I wanted to thank the organizers for inviting me. It would have been nice to be in Barcelona, but this is what we get these days. Actually, the first international conference I ever went to was the workshop in CRM in 2008. So it's kind of nice to be back, quote unquote. Yeah. So I'm going to tell you about this joint work with Nick Gursky and Niles Johnson, and there's a lot of really complicated definitions in all of this work. I'm going to skip most of those, and I just kind of want to tell you the overarching story. But if at any point you have questions, and if you want a more precise definition, just let me know, and I can say a little bit more. But I mostly want to give the context for the work, and then give a little bit of what we actually did. So let me start by, here we have my plan for the talk. So first I'm going to tell you about group completion and S inverse S. Then I'm going to tell you a little bit about opfibrations and Quillen's theorem B, and then I'm going to tie the two pieces together to give a little bit of an idea for the proof that S inverse S is the group completion. So in algebra, if I have a commutative monoid, M, we can construct the growth and the group completion. I'm going to call it GRM. And I mean, this is the universal object that does what you think it should do. So it comes with a map from F to GRM, such that if A is any abelian group with a map from M, then there exists a unique map from the group completion. So it universally adds inverses. That's sort of the idea. And another way to think about it is that this is just the left adjoint to the forgetful functor from abelian groups to commutative monoids. So it has this property. And we're pretty familiar with this. If we start with the natural numbers, with addition, we get the integers. If we start with the integers, -0 with multiplication, we get the rational numbers with multiplication. And maybe in a different realm, but equally important to the story, if I take projective modules over a commutative ring R, and I take the isomorphism classes, and with the operation given by direct sum, then this is precisely what gives me the K0 of the ring. So this is an algebraic story, but already thinking about this example of K theory of a ring, we kind of want to translate the story to the topological side. And what might that mean? Well, there's of course a lot of different answers, but one possible question is, well, what happens if I have a topological space with some sort of multiplication, and whether, like, if it doesn't have inverses, can I add inverses somehow? And I'm going to give you the topological group completion story about this. So topologically, if X is an A infinity space, and we know that roughly means that we have an operation that is associative and unital up to all higher homotopies. And if this space has inverses up to homotopy, and I should add here, we can actually just see this at the level of pi naught. So if I have an A infinity space, pi naught of X is a monoid. And then asking to have inverses up to homotopy means that pi naught is a group. Then there exists a space Bx such that X is homotopy equivalent to the loops on Bx, and this is basically Stashev's theorem. So up to homotopy equivalence, any A infinity space is a loop space as long as there are inverses. But what happens if there's no inverses? Well, if X doesn't have inverses, we cannot expect this to be true because we know that the loop space has inverses. So instead, we have the following, and this is just one version of group completion. So if X is an A infinity space that is commutative up to homotopy, I'm not expecting it to be for that homotopy to be coherent in any possible way. So I'm not asking this to be an E infinity space, not even an E2 space necessarily, just that the multiplication is commutative up to homotopy. Then there exists Bx with a map from X to the loops on Bx. And again, I cannot expect this to be a homotopy equivalence, but instead what is true is that for all commutative rings, K, I have an isomorphism homology. So here I have the homology of X with respect to K, and I'm going to localize with respect to pi naught of X. And I'll explain a little bit more about this in a second. And this is going to go to the homology of the loops on Bx. So what's happening here? Well, here I have the homology on X, the homology of X. Pi naught of X acts on the homology on X, and pi naught of X is a monoid. And then I'm just going to be localizing with respect to that action. So that's what's happening here. And then once I localize, I get this isomorphism. So this this is sort of like a generalization of Stash's theorem, and it tells us more precisely what's happening here. One thing that I want to point out is that you can get away without necessarily asking for commutativity. You could get away with a little bit less, but for the purposes of this talk, it's easier for me just to say commutative, but you can ask for a little bit less. So a couple of remarks regarding this. The first one is that pi naught of X, as I mentioned before, is a commutative monoid. That acts on homology. But 2 if I let k be the integers and take the 0th homology, we get that pi naught of the loop space on Bx is, well, maybe I can just write it this way since I introduced a notation, is the growth on the group of pi naught of x. So this space here has a property that in particular at the level of connected components is algebraically group completing x. But then there's this other rest of the homology property. And then the last remark that I want to make about this is that if Y is any space with a map from X to Y, actually say this way, with the following property, I'm going to call this property star, that so you have the map on homology, and if the map induces an isomorphism after localizing in the source, then Y has to be equivalent to loops B on X. And maybe something more general that I should say is that anytime that you have two spaces that satisfy this property star, they have to be homotopy equivalent. Of course, like this is included in the statement, but even if I didn't know of the existence of loops B on X, that would still be true. So this basically another way of saying this is that this property here is completely determined, like it determines the homotopy type of the space that you put in here. So this is maybe not so obvious because this is a statement about homology, but it turns out that it is enough to tell us what's going on. And in general, if we have such a property, we say, so for such Y, we say Y is the topological group completion of X. So why might one care about this? Well, for example, this is one way in which we can construct spectra out of E infinity spaces. So if X is an E infinity space, so now my multiplication is associative and commutative up to all higher homotopies, we can construct a spectrum, which I'm going to call boldface EX. And so the spaces of the spectrum are going to be X, BX, B square X, and so on. So basically, we can iterate this classifying space construction. And it is not quite an omega spectrum, but it's an almost omega spectrum. In the sense that if I take loops on Bn of X, this is going to be equivalent to Bn minus 1 of X for n greater or equal to 2. So we don't quite get it at the bottom, but from one point onwards, this works out. And basically, this is just Stash's theorem, because if we're looking at the spaces of the spectrum, they're all connected, except at the bottom possibly. So if you have something connected, it is group-like in the sense that the connected components form a group and not just a monoid. But moreover, so the one problem that we might have not to have an omega spectrum is precisely at the bottom where we have the map, but this map is a group completion. Which means that the loops on Bx is the zero space of the spectrum. So if I really want to understand the homotopy type of this spectrum that I constructed, all I need to know and understand is the homotopy type of the group completion. And another way of expressing that is that if I want to look at the homotopy groups, I'm going to write S here because we're taking the stable or like the homotopy groups of the spectrum just to distinguish them. This is isomorphic to just the standard homotopy groups of the space loops of Bx. And so again, this is a good way of constructing spectra for which we somewhat understand their homotopy type. To give you a very specific example, and we'll return to this example soon in a different context, but if I take X to be the disjoint union over n greater or equal to 0 of the classifying spaces of the symmetric groups with operation induced by block sum. So if I give you sigma n and sigma m, you map to sigma of n plus m basically by permuting in blocks. It turns out that this gives the space here any infinity structure, and we will talk about this a little bit more in a second. But basically, if you take the space, one way of interpreting the Barat-Quillen theorem is that Ex is equivalent to the sphere spectrum. And this is where you have to get somewhat excited and think about what this group completion is doing, because when I look at the homotopy groups, or maybe another way of saying is that the connected components of X are all k pi 1s. So they don't have any higher homotopy groups. And instead, so I did I constructed the spectrum, and I'm looking at its homotopy groups, but the homotopy groups of the spectrum are the homotopy groups, are the stable homotopy groups of spheres, right? Like those are like complicated and rich and carry a lot of information. And this was done just by this group completion, because I know then, so maybe this is what I should say, right? So like the homotopy groups of loose Bx are the homotopy groups of sphere. Let's write the word stable. So these are complicated homotopy groups, and that might be the understatement of the century, but they're complicated, and they sort of like came out of this group completion property. So group completion is complicated and mysterious, and every time, I mean, most of my work has revolved around working with group completion, and it's always really, really hard to figure it out. Now, one thing that you might want to do is you might want to start with some categorical data in order to get to any of these things. And one standard way in which we do it is if I start with C being a symmetric monoidal category. And then I can take its classifying space, and for the sake of not confusing all the different B's that might appear in the stock, I'm just going to write bars for the classifying space. But of course, this involves two steps. One is to take the nerve of the category and then take the geometric realization. But I'm just going to write it this way. And standard result by independently by Siegel and May is that the classifying space of a symmetric monoidal category is an E infinity space. Which means then that I can take what I'm going to call K of C, the K theory of C, which is going to be the spectrum associated to the infinity space given by the classifying space. So I can construct this K theory spectrum for every symmetric monoidal category. But as we just pointed out, if I actually want to understand the homotopy type of this spectrum, I basically have to understand the group completion of the classifying space. So it's homotopy groups are those of the group completion of the classifying space. So if C is a symmetric monoidal category that has inverses, you don't have to do anything because that's going to be group complete and you get what you want. But most of the time, our symmetric monoidal categories don't have inverses, and then the group completion is really what's telling us what's happening with that construction. So I want to give you a couple of examples before asking the main question. So if C is a category of finite sets and isomorphisms, then the classifying space is going to be precisely that space that I had talked about before, or up to homotopy, is the disjoint union of the classifying spaces of the symmetric groups. And then we get that the K theory of C is then the sphere spectrum. That's again pretty Quillen in a different way of thinking about it. But another standard thing that I might do is take C to be projective modules over a ring R. I'm only taking the isomorphisms. And then the K theory of C is precisely what we call the algebraic K theory of the ring. And what I'm giving you right now is a very ahistorical account, because really what happened is that initially people had defined K naught the way that I defined it earlier, and then there was K1 and K2, and then it was realized that if you actually did this construction, then the K1 and the K2 matched up as well. Well, K naught was kind of matching up by construction, but K1 and K2 were matching up as well. And this is a very deep theorem because it's kind of telling us that this group completion that was happening, that we're doing, is actually having this this effect. Again, another point to make, similar to what I said before, is that this homotopy groups are very complicated. They're rich, they carry a lot of information, and we haven't been able to compute them all. So again, it's telling us that group completion is mysterious and interesting and related to many other things. So we might want to study it more. So as someone who works a lot with categories, you might want to ask the following question. Can we construct group completion at the categorical level? And what I really mean by this is, can we construct a category whose classifying space will be the topological group completion? Your first attempt might be, well, let's just try to do something categorical. So maybe I have the category of symmetric monodal categories, and on the other hand, I have the category of symmetric monodal categories with inverses, and I have a forgetful functor, and I formally have a left adjoint. It turns out that is an interesting group completion categorically, but it's not the topological group completion. It doesn't really have the right properties. So you actually have to do something a little bit different. There's this wonderful theorem of Quillen. And I'm going to put Grayson's name here because the paper was actually written by Grayson. And I'm going to just change my notation slightly so that it matches my title and what people may have heard before. So if S is a symmetric monodal category, there exists a symmetric monodal category S inverse S, or S localized at S, as Joachim said when he introduced me, such that the following, and the map from S to S inverse S, such that one, so S inverse S has inverses up to homotopy. And here I'm working with categories. So what do I mean by it has inverses up to homotopy? I really mean that the classifying space, if I take the connected components, that this is a group. And I'm not going to write this down, but I might refer to group-like for this property from now on. And the second property is that if S is a groupoid, with faithful translation, and what that means is that the translation functor, so if I look at S plus dash, which is a functor from S to itself, I want that to be a faithful functor. So then if S is a group with faithful translation, then the map on classifying spaces is a group completion. So that's the S inverse S construction, sort of like the classical categorical one. Now, if you actually want to prove this, you can imagine that, well, my definition of group completion had to do with homology. So I need to figure out how to compute homology of categories and how to use the kind of like very, very explicit constructions that I had, which I'm not giving you right now, but you need to know how to compute that homology. So anyone who knows me knows that I work a lot in the world of two blank, and that was clearly in my title. So what I'm going to tell you today is about basically trying to generalize this to the world of two blank things. So trying to do this for symmetric monoidal bicategories or two categories. So just briefly, I'm going to tell you about symmetric monoidal bicategories / 2 categories. So a symmetric monoidal bicategory is a bicategory with an operation that is a pseudo-functor, and it has to be associative and unital and symmetric up to coherent coherent one cells, but then those one cells have to be coherent up to 2 cells. Like the definition takes pages and pages and pages, because if you think about the definition of symmetric monoidal category, for example, you have the pentagon axiom for associativity, and that's going to be replaced by a 2 cell that needs to be then coherent with respect to the other 2 cells that you might have. So this is a very, very complicated definition, and I'm not going to spend much time in this talk talking about it. There is a coherence theorem for symmetric monoidal bicategories that tells you that you can replace them with some that are somewhat strict and nicer to work with, and I'm not going to say much more about that. But basically, they're a little bit more manageable than just this very long definition that takes many pages. But to give you an example of one of these gadgets that you might care about, the prototypical example is the category of bimodules, or bicategory bimodules. So the objects are just going to be rings. The one cells are going to be bimodules. So to be more precise, if I want to talk about a map from R to T, is just going to be an RT bimodule. And then the 2 cells are going to be bimodule maps. The composition of one cells is given by tensoring the bimodules. And there's a symmetric monoidal structure in the whole thing given by tensoring the rings. And that gives you all the structure that you might want. Another example is cat. So this is the 2 category of categories. So the objects are categories. The 1 cells are functors. The 2 cells are natural transformations. And Cartesian product makes this into a symmetric monoidal category. So the theorem that I want to tell you about today, so Gursky, Johnson, and Osorno, is that it basically looks very much like the theorem I gave you before. So if S is symmetric, monoidal bicategory, there exists a symmetric monoidal bicategory S inverse S, such that 1 S inverse S is group-like, and 2, well, I should have said here that I also have a map from S to S inverse S, which is a symmetric monoidal map appropriately. So when I take classifying spaces, and I'll say a little bit more about classifying spaces of 2 categories in a second, or bicategories, but we have the map of classifying spaces, and this is a group completion. If S is a bigroupoid, so it has invertible 1 cells and 2 cells, and has faithful translations. So to prove this kind of theorem, like you actually first need to come up with an explicit construction and then try to prove that it has a homology property that I gave initially. So just to give you an idea, I'm not going to give you the whole definition, but to give you an idea of how one might come up with a construction that works. So the objects of S inverse S are pairs A1, A2, and S cross S. With the idea is that A1, A2 represents A1 minus A2. And this is the same way that you can do that. Growth and the group completion does precisely this, right? You're looking at formal pairs of elements and thinking of them as the formal difference. And then you just take an equivalence relation. Well, here, instead of an equivalence relation, we're just going to make that happen via the one cells. So the one cells are given by triples as F1, F2. So this is going to go from A1, A2 to B1, B2. So here, S is going to be an object of S, and F1 is going to be a map from S plus A1 into A2, and F2 is going into B1, and F2 is going to be a map from S plus B2 into B2. So you can see now that at least if I mod out by the morphisms, then I am going to be getting the growth, I think, group completion at the level of pi naught. So it accomplishes the right thing at the level of pi naught. I will not tell you what the two cells are, but what I will say is that if you're familiar with the one categorical S inverse S construction, in that one, the one cells look exactly, or the morphisms look exactly what my one cells look here, but then I mod out by an equivalence relation. Well, that equivalence relation, basically, I'm going to be seeing here at the level of two cells. And then my two cells are going to have to be up to some equivalence so that it actually works out, so that composition works the way that I need it to work. So in particular, and I'm not going to write this down, but in particular, if I take the if I take a one category and think about it as a two category with only identity two cells, my S inverse S construction is not going to be equal or even isomorphic, but it's going to be equivalent appropriately. So once because in one of the cases, I'm just going to have a one category thought of as a two category, and the other one, I'm going to have some two cells, but the two cells are unique. So you're actually going to get an actual equivalence. I'm going to pause here and see if anyone has questions. All right, well, I'll keep going, and I'm actually going to switch gears, and I'm going to tell you now about opfibrations and Quillen's Theorem B. So this is initially, it might seem like it's completely disconnected from the first half of the talk, but as I said earlier, I'm just going to tie them up at the end. So here my question is slightly different, and it's about what is the homotopy fiber of a two or just a functor. So if I have categories and I have a functor between them, I can take the classifying space. I want to identify the homotopy fiber. Or if I have two categories and I have a two functor between them, I want to identify the homotopy fiber. So this is something that people have studied a lot, and I just want to give you one sort of like an epsilon of pushing this a little bit farther in a very specific direction. So in order to do this, I am going to give you a slight definition for once. I feel like I've just been punting all the definitions today, but I'm going to give you something a little bit more tangible. So I'm going to tell you about lax comma objects. And maybe before saying anything, I should say that whenever you're working with two categories, you can take sort of strict limits and strict co-limits, but sometimes you can also want to take lax limits and lax co-limits, and figuring out which one is the one that you want to do for the specific purposes that you have. Like you just kind of like either have like really good intuition, or sometimes just have them all in front of you and then figuring out which one will have the right property. So in this case, I'm going to tell you about the lax comma objects which were defined by Gray, and the input is the following. So I have two functors. This is what I meant to say. So I have F here, and let's call this one G, and these are so F and G are two functors. And the lax comma object is an object here, which I'm going to call F little ROG, which comes with maps to C and E. Let's call this one a projection, so P sub C, this one's P sub E, and a lax natural transformation here. So lambda is a lax transformation, which has a universal property. So given another diagram that looks basically like this one, but now I have an arbitrary two category here. Oh, I wanted to call this one pi. And this one is the one that I'm going to call lambda. So there exists a unique two functor from K to the lax comma object, such that, well, the one thing that there's actually many things. Again, in two categorical land, you have more options than you might think originally, such that if you take the one for F, the diagram for F, going to G, so maybe I should really call it the diagram for pi, because that's the main character. And you whisker it with this map, and you get an equality of two cells. And this actually means I'm also asking for this to commute on the nose. So instead of asking, you could potentially ask to have some transformations here, but instead we're asking actually for these two pieces to commute on the nose, and then these two transformations to be equal to each other. So that's what this gadget is. And in particular, of interest to us, just given F from C to D and X an object of D, we have the diagram for F over X, which comes from looking at picking up the object X as a map from the point. And another thing that will be useful for us is that if phi is a one cell from X to Y, the universal property tells us that we actually have a map that maybe we should call phi lower star that goes from f over y, x to f over y. So let's say here by universal property. So the point of giving you this construction is that, well, it answers my question. So this is Quillen's theorem B for two categories. It's a theorem of Segarra. So what it says is that if f from C to D is a two-functor, and for all phi from X to Y, phi lower star from f over X to f over Y induces a homotopy equivalence on classifying spaces then we have the sequence of the inclusion, so not quite the inclusion, the projection of the lexical object into C and then the map into D. And I'm going to take classifying spaces. And the answer is that this is a homotopy fiber sequence. And you have to be careful about base points, but I'm not going to say much more about that. But there's something to be careful about there. So this gives a very explicit model for the homotopy fiber. And one question that you might ask is, well, when is the actual fiber the homotopy fiber? So when can we replace this lax comma object with the fiber over X? And if you've ever studied this question in the one categorical setting, the answer is, well, you need some lifting conditions to be true for your functor F. So answer, the lifting properties for F, and then to be more precise, if F is an up vibration. So I'm not going to give you the definition, the full definition of up vibration, because that basically would take me the rest of the talk and more. But just roughly, it means that if I have a one cell, F from Fx to Y, then this has a lift of the form F hat from X to X hat. And I left a space here because I want my lift to be up Cartesian. And up Cartesian basically means that the cell has some lifting properties of its own, meaning that some diagram is an appropriate pullback. And then similarly, I want lifts for two cells So if I have alpha, which is a 2-cell from F to F of G, then this has a Cartesian lift alpha hat from G hat to G. And I want to point out that there's this funny thing that's happening here, that for 1 cells, the source is the one that is in the image of F, and for 2 cells is the target that is in the image of F. And so there's, of course, like for any of these definitions, you could just like take ops in whatever way, and then you get other kinds of vibrations. But this is the one that would work for us. So this is the one that we're calling up vibration. And it is a generalization of one categorical of vibrations. They're all, and I should say, we did not come up with this definition. This is just a version of taking Buckley's definition and making it precise for the kinds of things that we had. So the theorem one of the theorems I want to tell you about today is that if I have a pullback diagram like this, so if F is an up vibration and the 2 cells of D are invertible, then I have a natural map that comes from the universal property that goes from the actual pullback, so the strictest possible limit that you can think about in 2-category land, so from the pullback of F and G to the lax comma object of F over G. And the statement of this theorem is that this is a homotopy equivalence. On classifying spaces. So this is a general statement about being able to replace the lax comma object with a strict pullback. Briefly mention that I can change this theorem if I don't have my cells here invertible. This is not generally true, but I could change the lax comma object with a pseudo comma object where everything that was a lax now is invertible, and then that I would still get this result.
Sorry, Angelica, can I ask you one quick question? It's a technical.
Yes, you may.
Yeah, so do I remember this correctly, that when you are trying to replace this over category with the actual pre-image, then you don't need the full power of this up vibration condition? Like, not all the lifts are necessarily to exist or something like this. Is that right?
I don't know. I mean, so so in the classical setting, I don't know. In our setting, for even like for the super specific example that we were gonna use it later, like we really need the lifts at all the possible levels. Like they actually get used. And actually, maybe I should say here. So in this theorem, this particular theorem here, the way that you prove this theorem is by actually constructing a map back, right? Like explicitly constructing a map back. And in order to explicitly construct the map back, like you actually use the lifts, right? Like that's really where the lifts are coming in. And I'm gonna venture to say, even though I'm not completely sure about this, that you probably have a statement of the sort that F is an up vibration if and only if for every diagram like this, you always have the map back, right? Like it's really like all the lifts, just like you see them coming in at all levels. And I'm obviously going to spare you the proof of this theorem, because basically like it's really pages and pages of, oh, if you give me an object here, I need to pick a lift. And then if you give me a 1 cell here, I need to pick a lift, and then I need to pick another lift that like relates it, so that like things eventually actually compose as nicely as they could. So it is, you really are using the lifts at all levels.
I see. Okay, cool. Thanks.
So in particular, we get a map from the actual fiber, which is the pullback in the case where we have the map from the point to the lax comma object, and that's an equivalence under of homotopy spaces on classifying space. So as a corollary, I get a version of Quillen's theorem B, which is that so if F is an up vibration, D has invertible 2 cells, and the phi lower star induce homotopy equivalences. Then we have a fiber sequence with the actual fiber. Let me put classifying spaces already to make my life easier. So this is just giving us another way of thinking about Quillen's theorem B, but one that sometimes, like, the fiber is a little bit more easier to handle, but of course this comes at the price of having an up vibration. All right, I'm going to pause and see if anyone has any questions. All right, so we have arrived to the third part of the talk, which is the proof that S inverse S is a group completion. So I'm just going to jump in and give you another theorem, which is the following. So if F from C to D is an up vibration, D with invertible 2 cells, then there exists a spectral sequence where the E2 page is the homology, the pth homology of D with coefficients in what I'm just going to call now curly H sub Q of F inverse, and I'll explain what this is in a second, which converges to the P plus Q homology of C. Now, these are 2 categories, so I think I need to explain a little bit what I mean when I write any of this. So what is all of this? Well, I'm going to explain in general what homology of a 2 category with some coefficients really means. So the first thing is that we really mean the homology of a simplicial set, which is the nerve of D. And now I'm going to tell you a little bit about how the classifying space of a 2 category goes. And I should say that there's there's many different constructions of the classifying space for a 2 category. They all end up being homotopy equivalent, but here we need an explicit construction. So here we have this simplicial set. So here the P simplices are 2 functors from what is called the oriental category of P into D. I'm going to call this sigma here. So this is the oriental, so streets oriental. And basically the idea, for example, just to draw what O2 looks like, you're going to have, it's kind of like the simplex category, except that you allow for 2 cells. So here you have a 2 cell that goes like that. And then if you're looking at O3, you're going to have this tetrahedron where like the two faces have to be equal to each other. So I'm taking homology of simplicial sets with local coefficients. So the coefficients are local coefficients. So here I'm calling this one M, which is a functor from the category of elements of ND into abelian groups. So here, this is the category of elements of the simplicial set. And this is how you take, like this is in general how you do homology of simplicial sets. And it has the property that, so if my local coefficients happen to be morphism inverting, meaning that if any map here gets sent to an isomorphism, then it will actually induce local coefficients on the classifying space. And then I will be thinking about the usual homology of topological spaces. So just a brief reminder, because it's going to be slightly important. So the objects of the category of elements are pairs P, sigma, where, well, P is some natural number and sigma is an NP of D. And then a morphism phi from P sigma is always going to land in P prime phi upper star of sigma. So phi here has to be a map from P prime to P in delta. So maybe I should have said this in a different order. So the maps here are basically maps in delta that match up the simplex appropriately. So my local coefficient system, HQ of F inverse, is the following. So I need to tell you where P sigma goes. It's going to go to the Qth homology of F inverse of sigma evaluated at 0. So let's actually make sure that this makes sense. So sigma here is a 2 functor from the oriental category into D. So in particular, it has an object 0. So I'm taking sigma 0. Now that's an object here, and I'm just taking the fiber with respect to F prime, and then I'm just taking the Qth homology. That's what my local coefficient is. Then I have to tell you what happens to maps. So phi from P sigma to P prime phi upper star sigma goes to, or is induced by the following. So I have the fiber of sigma of 0. This is equivalent because we have an up vibration to the lax comma object. The lax comma object is going to come with a map that I'm going to call phi here, which is induced by my map phi as well, which goes to the lax comma object here, and then this again, this is equivalent to the actual fiber. So this is what this is being induced by, and it's not hard to check that this is actually a functor. So this is the local coefficients that we have. So we have the spectral sequence in general, and now homology appeared again, which is what I wanted because I want a proof of something. So I can now give you the proof of S inverse S being the right thing. So I'm just going to list the ingredients. I'm not going to go into the details, but the first ingredient is that, well, we have S inverse S. And I didn't quite tell you, but there's also something called S inverse of a point. The construction can be done not only on S itself, but actually on any two category on which S acts appropriately. And I have a projection map. I'm going to call that rho. And it turns out, and this is one of the hardest things that we had to do for this paper, is to prove that this is an up vibration. And moreover, this part is not hard, but it is true that S inverse of a point has invertible two cells. So we can apply the spectral sequence. I'm not going to use the symbol because I'm going to use it for the spectral sequence. So we have a spectral sequence with E2 page, the homology of S inverse S, S inverse of a point with coefficients HQ of rho inverse and converging to HP plus Q of S inverse S. The second ingredient is that for any object in S inverse of a point, the fiber is isomorphic to S. This is, again, the construction is so explicit that this is not hard to show. And then via this isomorphism, the local coefficient system HQ of rho inverse. Well, so what's happening here? So now I'm originally I was sending P sigma to the Qth homology of I have it here. So the Qth homology of rho inverse of sigma evaluated at 0. But now I'm saying that no matter what I have, this is always S. So this goes to the Qth homology of just S. And the first thing that you might wonder is, like, do I get a constant coefficient system? And the answer is no. But I can explicitly compute the maps in this coefficient system. And I'm not going to tell you what the maps are, but the maps are given or are induced by multiplication by elements of S. And this is important because then I can localize the spectral sequence with respect to pi naught of S. And you have to be careful that like everything in the spectral sequence is actually well behaved with respect to the action of pi naught of S, but it turns out it is. And so we get this spectral sequence where now I have, I'm going to call this, so I have the pth homology of S inverse of a point with respect to some coefficient system that I'm going to tell you about in a second. And then I have the homology of the people's Q homology of S inverse S, localized at pi naught of S. But because this gadget already had the action of pi naught S was already invertible there, then I didn't really do anything. So I just get back the homology of S inverse S. And in here, LQ is, well, it's just this coefficient system that I had before, but now localized. And I'm not going to write down what's happening with the maps in this coefficient system, but again, are just given by multiplication by elements of S. And that actually becomes important because now I inverted multiplication by elements of S, which means that my maps in this coefficient system are actually isomorphisms. So that means that when I look at classifying spaces, I have coefficient systems the way that I think about them with in topology land, which means that the fact that this guy here is contractible tells me everything that I need. So that's the last ingredient, is that S inverse of a point is contractible. LQ is morphism inverting. So HP of S inverse of a point with coefficients in LQ is just going to be HQ of S localized at pi naught of S inverse when P is equal to 0, and is going to be 0 when P is greater than 0. So the spectral sequence collapses, and we just get the isomorphism that we wanted, and that's the end of the proof. And I cannot believe that I actually finished at 11:29, so I'm going to stop here.
Thank you very much. So, are there questions or comments?
Go on then, I'll start.
Yes, please.
So one big question and lots of little ones to go with it. So the big one is what you do for generalize from one category to two categories to construct S inverse S. Do you think there's an infinity version?
So I haven't thought about this, but there should be. And so we do it very explicitly, and basically, so the way we did it is we look at the one categorical version, your 0 and 1 cells are the same. And then in the one categorical version, you had an equivalence relation in 1 cells that now we're actually keeping track of. And in our definition, we had an equivalence relation on 2 cells that you could keep track of, and then have if you had 3 cells, right? So you could probably do this all the way. If you want to do infinity category version, though, you don't want to sort of like do this 1 by 1 step kind of thing. You probably want to do a whole thing. So
No, I mean, I wouldn't ask you to do 3 categories or 4 categories, but I mean,
but yeah, if you want to do infinity so if like what I'm saying is, so this is what our step-by-step was, right? So if you actually want to do it with infinity categories, you probably want to take this intuition and figure out exactly how you would do it explicitly, and probably like a universal property is a better way to think about it in once you're doing it for infinity categories.
Okay, and then I just had some really technical questions which would probably be of interest to nobody at all. So your definition involving, I mean, the definition of the 2 nerve, you said there's lots of equivalent or lots of different definitions. Is the one you gave the same? You said 2 functors from the Oriental.
Mm-hmm.
Is that the same as saying lax functors from the Delta?
Yeah.
Okay. Mm-hmm. The other question is the homology you're doing. I mean, once you've taken the 2 nerve, once you've got the simplicial sets, is then the homology of the Gabriel-Zisman homology?
Yeah.
Okay. Thanks.
Can I ask a question?
Please.
So
go ahead.
I mean, I don't know if this is a sensible question, but I'll try. So if you take one of those examples you talked about at the beginning with the bimodules or something, you know, like explicitly just take S being one of those. Do we get, I mean, is this space then what you are making should see something about algebraic K-theory, doesn't it? Like of, I mean, how
so
rings together somehow, but you know, right?
So that one, if you make slight modifications to that one, you see the Picard group of the ring, you also see sort of like the units of the ring, which maybe they're not that interesting, but this is sort of like if you actually don't have to do group completion because like you already like decided to take only invertible objects. If you don't do that, so
category would you take now? What are the objects? Just rings, right?
So for example, I can, yeah, maybe I should back up. So let's say that I have a specific commutative ring, and I'm going to take the objects to be algebras over that ring.
Okay, cool, yeah.
And if I restrict to Azumaya algebras, which are basically the ones that are already invertible, then you're just going to get the Brouwer group, and then you're going to get the Picard group, and so on. But one thing that I haven't thought about, and I think it would be interesting, is so like if instead of doing that, if you actually have to group complete, so do not restrict to Azumaya algebras, what happens when you do these kinds of things? Because then you're creating higher homotopy groups, and that could be interesting. So, but that I think that's a good question, and I just don't know the answer to that.
That's cool. And just a follow-up question right away, because you now explained this to me. So. I mean, classically, I mean, maybe I remember this wrong, but if I remember in Grayson's paper and some others, he also uses the same technology to establish some version of localization sequence. Anything like this you have thought about in this setup?
We haven't thought about, but it's kind of like in the pipeline of like what else we can do with this, because at this point we just have this like very explicit construction. The reason we started working with this is because we thought we needed it for our stable to type project. We couldn't use it there, but we still decided to write it up. But like there's consequences of this that I personally haven't thought about, but well, Niles is here, and I don't know if he wants to be not so shy and show his face, but he has thought a little bit more about this, and he's also thought about like how this could aid with computations of some K3s of certain things, because you can use the S inverse S construction, the classical one, to compute explicitly some K2s. So if you're one level up, then you might expect to do some K3s, but I don't know if Niles wants to be to show his face and say a little bit more about that. But I personally haven't thought about that.
Hello, everyone. And Angélica is correct. Yeah, you can see some of the higher K theory groups, which I think is super neat.
I see. Cool. Great, thanks.
Are there more questions? Well, otherwise, I think we should just thank Angélica again and call it a day.
Thank you.
It's late for you guys. Thank you. Everyone in Europe, just go to bed.